So he will talk on a moduli space for rational elliptic surfaces of index 1 and 2.
Thank you. Thank you. Thank you all for coming today. Thanks very much to Mina for organizing a wonderful week here. And weekend too. This is joint work with Alina Zambanini, who is a postdoc now at the University of Leiden. She just finished her PhD at Penn earlier this year. So I'll give a little bit more about the history, how we got to working together after a bit. So what are elliptic surfaces? What are rational elliptic surfaces? What are indexes? So an elliptic surface is a surface with a map to a curve whose general fiber is a genus 1 curve. So, and we're going to assume it's relatively minimal surface. So that means there might be -1 curves on the surface, but there are no -1 curves in the fibers of the map. If you find a -1 curve in the fiber of the map, you can contract it and you still have the map. If you have a -1 curve that is dominant, you better not contract it, you lose the map. So you can always contract -1 curves in the fiber and obtain a relatively minimal model for your elliptic surface. We're going to talk about the case when the surface is rational. It's a rational surface, so it's a blow up of the plane, essentially, turns out. And we'll assume it's smooth, so we've resolved any singularities. And we'll call that a rational elliptic surface. If X is rational, it forces the curve, the base curve, parameter space of the fibration to be a P1 to a rational curve. You can't have higher P's. And the canonical example of producing such a surface is to take two cubics in the plane, and they will be generically 9 times, and then 9 to the center. And you blow up the 2 cubics form a pencil of cubics. You blow up the 9 base points, and you get a fibration. And the pencil is parametrized by P1, so it's clearly a rational surface. It's a 9-fold blow-up of the plane. And the cubic general member of the pencil is a cubic curve, which is genus 1, so it's elliptic surface. And it's easy to see it's relatively minimal. These surfaces, you get this way, always have a section. When they blow up let's say you blow them up in some order, the exceptional curves form 9 different sections, right? And the cubics sort of separate when you blow up. And so there's a section of the fibration when you start with a pencil of cubics. That's not always the case. So it's been classically known that every rational elliptic surface is obtained by a pencil, but not necessarily of cubics, of curves of degree 3m, cubics, sextics, nonics, etc., with 9 base points. It's like this, but the base points have multiplicity n in the pencil. So when m is 1, you have cubics. Well, when m is more than 1, you don't have cubics. And the case when m is 2, for example, is the case of sextics. So you have essentially sextics with 9 nodes, right? 9 of these. 9 double points. And you take, assuming try to build a pencil of such, you fix the 9, if you fix the 9 points, you can hope that maybe there's a pencil of sextics double at those 9 points. That's not always the case. And then you make the same construction, but you don't have any section. The 9 blowups are bisection. And in general, that's the m equal 2 case. So m equals 3, you have curves of degree 9 with 9 triple points. And m equal 4, you have curves of degree 12 with 9 quartic singularities. multiplicity 4, etc. And in this case, when m is 2 or more, there's always a multiplier because there are 9 points here, and there's always a cubic through 9 points. General cubic through 9 points. So there's always one, and that cubic, if you take the cubic through the 9 points, so take the cubic and take it with multiplicity m times the cubic, that is a member of the pencil. That will be a member of the pencil. So the double cubic is a sextic, which has multiplicity 2 at all the points. So it gets into the pencil. When you blow it up and resolve the pencil, the multiple cubic becomes a multiple fiber of the elliptic fibration. That's an example of multiple fiber phenomenon in the elliptic surface. So that's one of the possible fibers classified by Kodaira in the 50s. He was able to classify all of the possible singular fibers of a rational elliptic surface. And I've drawn them here. They correspond to the many of them to the Lincoln diagrams that we saw yesterday. Now to stop. And I'll begin the notation. I0 is just a smooth curve, so it's not singular. All the other ones are singular. And IN is a cycle of rational curves. So that can happen. For example, in a pencil of cubics, you could have a triangle. When n is 1, it's not a cycle, it's just a nodal curve. N equals 2, it's 2 curves that meet in 2 points. Beyond that, it's a cycle. You could also, for any of these could occur as multiple fibers, just as the smooth one showed up here, but in fact, you can have multiple fibers of cycles. Cycles can be multiple. No other of the possible singular fibers can be multiple. There are 7 other types. The IN star fibers are chains of P1s of multiplicity 2, n plus 1 of them, with 2 multiplicity 1 components on each end of the chain. So 4 multiplicity 1 components in total. Those cannot be multiple if they occur. Then you have these, the 2, 3, and 4 fibers, which you see easily in the plane as cubics, a cuspidal cubic, a line, and a chronic, 3 concurrent lines. Those are possible. Those are possible on general elliptic surfaces. And then you have 3 additional ones. The 4-star, 3-star, and 2-star that correspond to E6, E7, and E8 extended Lincoln diagram. Each one of these is possible too. And I mention this because in detail because I'll explain in a second. So how many parameters are there for rational elliptic surfaces of index m? Well, when m is 1, there's lots of ways of arriving at this number, but basically, you can ask how many pencils of cubics are there? Right? So up to automorphisms of the plane, and if you can count that, there are 8. It's an 8-dimensional family. You take the space of cubics. Cubics is a 9-dimensional linear system in the plane. A pencil of cubics is a line in that 9-dimensional space. So you have a Grossman of lines in P9, but you have automorphisms of the plane that act, and when you subtract the automorphisms, you get an 8-dimensional space. For all of the higher index ones, it's a 9-dimensional space. Make this more or less the same kind of calculation. So I want to just recall that I worked on this for my thesis, and I tried to work out the moduli spaces in the sense of geometric invariant theory for the m equal 1 cases, and I did it in 2 different ways. So I looked at pencils of cubics So I looked at this Grossman of lines in the P9 of cubics, and I calculated which ones were stable in the sense of geometric invariant theory for the natural action of the automorphisms of the plane lifted to SL3. And I got an answer. And, it involved the criterion for stability involved the existence of bad singular fibers. I'll mention that in a moment. Then in another separate attempt at trying to understand these, I looked at the Weierstrass equation. So if you write any cubic curve in the Weierstrass form, y squared equals a cubic, you can eliminate the squared term with a Turnhausen transformation, and you have y squared equals x cubed plus ax plus b. If you let a and b be functions of a parameter t, that gives you the family of, and when a is, and the degrees then of the polynomials a and b tell you which is basically related to the geometric genus of the surface you get. When the degrees are respectively 4 and 6, they're rational. So the rational surface here. And so this is a little bit simpler analysis to understand the geometric invariant theory. Now you only need to look at SL2 actions because you only have basically the automorphisms in P1, the T space. On the other hand, there's extra information here because in order to write down a Weierstrass equation, you need to have a section. The section is the point of infinity of the cubic curve that is only given here by an affine equation for the cubic. Is the section is the point of infinity, exists for all t. But basically, what was interesting at the time was that I got the same answer. The stability of the surface was related to the existence of bad singular fibers. About 20 years later, Heckman and Looijenga returned to the problem of constructing moduli spaces for these things, for the rational elliptic surfaces with a section. They took a different approach. If you look at the discriminant, which is polynomial of degree 12. So A is degree 4, B is degree 6. The discriminant for a cubed plus 27b squared is degree 12. It turns out that you can't get every degree 12 polynomial as a sum of a cube and a square. Okay, you can only get there are 12 dimensions of polynomials in degree 12. You can only get 11 dimensions worth of. There's an 11-dimensional family of polynomials of degree 12 that can be written as a cube plus a square. So this hypersurface in here, they took that approach of understanding the geometric invariant theory for divisors of degree 12 on P1 restricted to this hypersurface. They got a blow up of the moduli spaces that I constructed. And they were able to do a slightly better result. They were able to prove the moduli space is rational using their approach. I had not been able to do that. Well, this is the answer. Okay. That when n is 1, when you have a rational elliptic surfaces with a section coming from cubics or Weierstrass equations, coefficients degree 4 to 6, they're stable if and only if all the singular fibers are reduced. Reduced singular fibers. So that means when you go back to the list of singular fibers, you can't have any of these IN star fibers because they're not reduced. These fall in the interior here of multiplicity 2. These are allowed, but none of the E6, E7, or E8 fibers are allowed. Those are the stable ones. And then the semi-stable ones, the IN star fibers were allowed. This one's based on the but not the E6, 7, 8. So that was the answer that I got. And these are the unstable ones. Well, 2-star, 3-star, 4-star. And as I say, I get the same answer in both of these approaches for the pencils and for the bar stress equations. So, so I've done this work. Heckman and Looijenga 20 years later did this refinement. Great paper. And then last year, colleague of ours, Antonella Grassi, a professor at Penn, who just has moved to Bologna now, wrote to me. And she said, you know, I have a student who's writing her thesis on the m=2 case, and she's come up with criteria for stability. And she took the analog of the pencils of cubics. So the m=2 case are sextics with 9 nodes. Okay. And then if you look at the double cubic through the 9 nodes, that's the double fiber. And so she analyzed the geometric invariant theory of SL2, actually, the automorphisms of P2 on, first of all cubics, all sextics, and then all pencils of sextics. So it's sort of the Grossman of lines in the projective space of sextic curves. And then she took that analysis for the geometric invariant theory on the Grossman and restricted it just to not to all pencils of all pencils of sextics, but only pencils of sextics with 9 nodes. And you get an answer. And it's complicated. And she did a nice job in understanding it's sort of related to the log canonical threshold singularities that appear. And so Antonella said, why don't you reach out to her, read her thesis, and so I called her up. I zoomed her up. I should say. Call people these days. I zoomed up Lena, Antonella student, and we had a nice conversation about her thesis. And then, so I invited her to give a Zoom talk at Colorado State, and she gave the weekly colloquium last spring one afternoon. And so we got to talking, and she asked me this question: so I did, Rick, I did the analog of this. Is there an analog of this? And we write down something like a Weierstrass equation for this, and do an analysis. And I hadn't really thought about that, but let's try. And that's what came out of that is what I'll tell you about the rest of the hour. So in the m=2 case, let me we sort of approached it by, the Weierstrass equation requires the existence of a section, and it's part of the data. The Weierstrass equation, you give yourself a section, and in that section, you put that section at the point of infinity, and you write that in the equation. And so we took the same approach. In the m=2 case, you always have a bisection, because if you blow up the 9 points, the last blow up you make is a -1 curve, which meets all of the fibers twice. It meets the cubic once. It's a double cubic, so it meets that fiber twice too. So we're going to look at pairs, which is a rational elliptic surface of index 2 and a pair and a bisection, and try to mimic the Weierstrass equation approach for that modular problem of classifying pairs, rational elliptic surface with a bisection, chosen bisection. Let F be the multiple fiber. Now the bisection is a curve that goes across, but meets every fiber twice. And so you get a divisor of degree 2 on each fiber. And a divisor of degree 2 on a genus 1 curve gives an involution. Namely, you have say that x is related to a point y when x plus y is linearly equivalent to that divisor of degree 2. If any divisor of degree 2 on a genus 1 curve moves in a pencil, and so you get a pencil of divisors of degree 2. Every point is part of one of those divisors of degree 2 and is then therefore paired with its mate in the divisor of degree 2. There are 4 fixed points, but that gives an involution. And that involution on the general fiber extends to an involution on the whole rational elliptic surface. So the general property of rational elliptic surfaces, rational maps. And so you get, if you take the quotient of the surface by the involution, what you get is the quotient on each fiber, you get the quotient by this involution, which gives a P1. Quotient of the elliptic curve by this involution is rational. And so you get a ruled surface. And the fixed points contain a foresection because on the general fiber, there are four fixed points for this involution, namely the 4 points of order 2, basically. Choose one when it's 0. And so you have a foresection. That foresection, of course, meets the double cubic only twice. Meets the sextant. It turns out that therefore there are 2 isolated fixed points on the cubic that comes additionally, and B passes through one of them. Those isolated fixed points give singularities of this ruled surface here. And let me draw you a picture here. Try to do that here. So over here is your rational elliptic surface, your double fiber. Here, here's your bisection. It only meets the double fiber once. Meets the general fiber twice. Here's the ramification locus. This is generally the 4 points that are fixed under the involution. And when you divide by the involution, you go through a ruled surface. You have the ramification curve turns into the branch curve of the double cover. The bisection turns into a section. And the double fiber turns into a double P1. And then there are these 2 isolated fixed points to the involution that come in. You have to have 4 points on each fiber. Only 2 coming from the branch curve. Well, so wait a minute, Rick. Ruled surfaces don't have double fibers. What do you do? They don't have double P1s, but this is a singular one, so it can. And it's easy to see how a double curve might show up when we have these two isolated points that are fixed by the double cover. We have to blow them up, and when we resolve the singularities of this surface. This surface has singularities. When we resolve them, the A1 singularities turns into -2 curves. That's the resolution. That happens to 2 of them, and the old fiber turns into a -1 curve. And so now this is recognized as a singular P1, and the singularities. And this is a double member of the fiber. And so you can blow them down. You can first you blow down the double member, and you get the two -2 curves both turn into -1 curves. Then you blow down one of them, and then blow down the one that meets the section. And what you get when all said and done is now you have a minimal surface. The branch curve has, well, when you did the first blow up, it required a node. When you do the second blow up, it requires a tack node. And then the tack node is vertical. Blow down this -1 curve. And now this is a minimal ruled surface. The H then gets collapsed into here. It becomes a section that passes through the tack node at orthogonal direction, so to speak. And so now you have this configuration. And this turns out to be P1 plus P1. C has by degree 4, 3. H has by degree 1, 0, and the fiber has by degree 0, 1. And that is the description of the branching of the given by the natural involution that you get. So the theorem that sets us up to do this analysis that So this surface is P1 cross P1 as A indicated. C is a by degree 4, 3 with that vertical tack node. X is the double cover of P1 branched along that tack nodal curve plus the fiber. So throw in the fiber too. And that's a curve of type 4,4. Now, and it has a singularity. So when I say X is the double cover, I mean, you take the double cover and you resolve that singularity. That singularity is an elliptic singularity. Resolve it. And then B, the bisection, is the pre-image of the horizontal section. So the fiber gives you basically the double fiber, and the section gives you the bisection. And so you can rephrase this all as that there's a one-to-one correspondence here between rational elliptic surfaces of index 2 with a marking of a bisection and these kinds of curves on P1 cross P1, type 4,3, vertical tack node, etc. Having only sort of mild rational double point singularities otherwise, and it should not contain. It shouldn't contain H because that would spoil the existence of a bisection. It shouldn't contain the fiber because that would also spoil it. So you see that so we sort of reduced our moduli problem to a moduli problem of curves of P1 cross P1 with a set of open conditions. Okay, so you can't have two singularities, can't be too bad, and they can't. Certain coefficients can't vanish, otherwise. Contain those two curves as components. All right, so let's think about equations for this curve. So the curve, I mean, H was a horizontal curve and C is a type 4,3, so it meets it 3 times, right? But it meets it twice at the tack node, so there's one other point where it meets. There's one other point there. Let's call that point Q. So I have the tack node. Here's my fiber. Here's the tack node here, and the curve C meets, and then there's the horizontal fiber here, and it meets at one other point. We call that Q. It's P. Now, I want to choose coordinates such that P is at the origin of one coordinate system, Q is at the origin of another coordinate system, F is defined by one coordinate equals 0. H is defined by the other coordinate equals 0. It's easy to do. And you see that because it's a type 4,3, you can arrange the equation for C, which is bihomogeneous, by degree 4, 3. It's got degree 3 in the UV coordinates. It's got degree 4 in the XY coordinate system. And when you fill up the matrix of coefficients for this, a bunch of things have to vanish. All these coefficients in this corner have to vanish in order to get the vertical tack. This guy has to vanish in order because the C passes through the other coordinate point Q. And there's one other thing you can make equal to 0. It doesn't have to be, but it's convenient. You can make this coefficient 0 too. For this, it's exactly the same as the Weierstrass equation not having a square term. Okay? You can do a translation in X so that your y squared equals X equals a cubic. That cubic doesn't have a square term. You can change coordinates and make this second to top term non-zero here. Now this guy can't be 0, and this guy can't be 0. Those are the conditions that C doesn't contain either the horizontal or the fibrous components. And so what's left, if I make these things 0, what's left is 12 coefficients. And I've spoiled all of the automorphisms possible by choosing coordinates, except for the homotheties in the XY, the homotheties in UV, and the overall homotheties in the description. So therefore, what we see then is because of this, what we have is that rational elliptic surfaces of index 2 with the marking of a bisection are one-to-one correspondence with the 12 coefficients that are left modulo GM cubed. It's three multiplicative groups that are left in the automorphism space. So it's just an open subset of that because we have the requirement that certain coefficients can't be, certain things cannot be zero. So, and so, like I said, the GM squared are automorphisms coming from automorphisms of P1 plus P1, preserving that form of the coefficients, and then a third GM from the homotopy of the overall equation. And so the RST action on the three coefficients, the R is the homotopy, and the S and T are the two actions, either the XY or the UV coordinate systems. And I had conveniently indexed my coefficients such that they measure the XY and the UV degree. So it's pretty simple in that way. Now, you see now the 9-dimensional space. 12 minus 3 is 9. At least the right answer for the dimension. It's a little easier approach, though, because two of those coefficients can't be 0. We can use the automorphisms to make them equal to 1. Like, the automorphisms are scalars, right? So in both directions. So I can set them equal to 1. These two coefficients, and only get 10 coefficients, 10-dimensional space of coefficients. And then I can ask, okay, what's the automorphisms that are left that preserve that form of the equation where those two coefficients are 1? And it turns out it's not GM, fortunately a GM on Z12. And the reason is because these indices are both even. All the numbers are even. So there's a Z2 action that's left over even after the homotopy. So, and here's the explicitly, if you take a non-constant number T and then plus or minus 1, it acts this way. T to the 2i plus j minus 4, and then you multiply by epsilon to the I, plus or minus 1 to the I. That's the action. And it's not hard to see that the stabilizer subgroup that fixes the forms of the coefficients are RS and T look like this, and here's the plus or minus is the epsilon. So another approach would be, okay, instead of doing A12 mod GM cubed, look at A10 mod GM modulo this stabilizer subgroup for that form of coefficients. All right, that did sound easier to us, so that's the way we went first. Okay. And it's almost a weighted projective space because the GM is acting on the coordinates just with different weights, right? But it's not a weighted projective space because you have the Z2 action. So, and these two things, it's a direct product, so you can take the in either order. We decided to do the quotient in 2 steps. You could either take the weighted projective space and mod by the GM action, and then look at the Z12 action on that weighted projective space. That. Or the other way around, which is what we did. First, mod it out by the Z12 action, and then we asked ourselves, how do you mod by the GM? Yeah. When you mod out by the Z12 action, that's easy because it's diagonal. Some of the coordinates are multiplied by 1, and some of them are multiplied by 1 minus 1. The ones that are multiplied by 1 are invariant, get into the invariant subring. The ones that are multiplied by minus 1, the quadratics get into the invariant subring. So very easily write down the invariant subring. It's the sort of monoid ring generated by either the invariants or the products of the two that are anti-invariant. And this isn't exactly an affine torque, right? That monoid is a cone. appropriate space. So you have an affine toric variety. It's not affine space, but it's a single code. Maybe I don't need to go over the details of this. But, here are the invariants, the Wij's, and check that the polynomial of these Wij's get into monoid if and only if satisfies some inequalities to make sure that the original thing's a polynomial. And so that those inequalities define a cone. That's the affine toric variety. And now you want to take, so you have the affine toric varieties, that's the quotient by the Z mod 2 action. And now you want to mod by the GM action. And that's just going from affine space to a proj, from spec to proj, right? You have a grading here. According to these weights, because you know how T acts is 2i plus J minus 4. So every one of the variables has a weight, and you just take proj. That's a great answer. Okay. Proj of an affine toric. So it's toric, and therefore it's rational. It's get that immediately. That's great. On the other hand, it's not complete. It's not a complete toric. This proj is not. It's a nice example of a proj that's not projected. And why? Because it has. How do you? If usually the projes are complete when you take a graded ring, and you have the degree 0 part, the degree 1 part, etc. You form the proj by inverting something to take the degree 0 part, and that gives you the coordinate ring of that open set. There is a degree 0 part that's not constant. Namely, this one little invariant W12 has degree 0. So it has degree 0. So you have a whole polynomial ring in degree 0 that occurs in every open set. It gives you basically a function on your quotient, on your proj, and therefore it's a non-trivial function, so it can't be complete. And by the way, we weren't expecting it to be complete, right? Because when I imposed this the problem forbade certain curves, namely that we knew we were going to get an open set or something. So I wasn't completely surprised when you really enforce that by setting those things equal to 1. This W12 is a nice invariant. It measures the J function for the double function. Nice formula for it. It's a bit of a curiosity. All right, so now what about complete moduli spaces? So how do we complete this? And this is the kind of problem that Alina did for her thesis. She worked out the geometric invariant theory for sets of pencils, and they said you get criteria for stable pencils and semi-stable pencils, and therefore you have, at least abstractly, you've constructed a moduli space by taking the semi-stable pencils. But and there are her theorems from her thesis indicated that the stability was related to the singular fibers of the pencils. Not a surprise given the work on the m=1 case, Weierstrass vibrations. But it's not very explicit. You calculate stability and you don't really know anything about the space. So particularly don't know whether it's rational or not. So what we decided to do is, in order to compactify the space we just constructed with the A10 mod GM cross Z2 method, let's go back to the A12 mod GM2 approach. Let's see what can we do there. Let's return to the full double cover representation, where we don't ask for any constraints on the coefficients. We just take this set of 12 coefficients, which are arranged in the matrix that occur naturally by degree perspective, apply the GM cubed action, which is the diagonal, and ask what is the quotient of A12 modulo GM cubed here. And so it turns out that people who do toric geometry and they know how to take these quotients. So all the technology was available for taking GN to the R quotients of affine space if you can diagonalize the action. And I'll just go quickly over how that works. You basically choose a character of your GM cubed. So that's always in the form of this kind of form of RST goes to R to the alpha 1, S to the alpha 2, T to the alpha 3 for some triple of integers, alpha 1, alpha 2, alpha 3. And then you call a monomial in your, so Aij are the coefficients, so those are the variables of the problem. You declare a monomial to be alpha homogeneous of degree D when it satisfies this equation. So this equation, these are just the degree with the R variable, the degree with the S variable, and the degree with the T variable. Okay. Just wrote it out explicitly. So you ask that those 3 degrees be the same, namely D times the character function. And so you look for solutions to this, and you let SD be the solutions, the alpha homogeneous degree D solutions to this. You get a vector space, and they organize themselves into a ring. You take the sum of the vector spaces, and you take basically product of this ring. And this has an explicit toric description, and let me tell you how that works, because it's related to the construction. So you basically, you have this map that we had this little 3 by 12 matrix that sort of defined the characters of whether something was alpha homogeneous. You look at that map that's a map from Z12 to Z3, and you look at the kernel. Okay, that kernel is rank 9, and you choose a basis for it. Okay, so you get a 9 by 12 matrix. The rows form a basis for this kernel. And then it turns out that certain subsets of the columns of that matrix define cones in R9. And that gives you a fan, and that gives you toric variety. And that toric variety is the quotient space. Now, it would take a week not a week, it would take 3 hours of lectures to describe why that's true. But for us, we have everything very explicit. The rows of this matrix are the kernels. There are 9 rows. This is the kernels. You have these sort of 4 columns here at the beginning, and you have a bunch of identity up there. So the recipe for the cones, how do you tell which columns to take to generate the cones in the toric quotient? Here's the recipe. You take a point B economist, you dehomogenize the character. So instead of alpha 1, alpha 2, alpha 3, you divide through by alpha 1 and get 2 rational numbers. Alpha 2 over alpha 1 and alpha 3 over alpha 1. Let's call that number B comma C. Get a rational point in the plane. And then we're going to say that that point is in the strict convex hull of a set of coordinates ij in R2. If you can write it as a linear combination of those elements which sum to 1 and have strictly positive. You're not allowed to have any zeros in the way you write it. So it has to be kind of in the strict interior, so to speak. And so the recipe for finding the cones that apply, you fix your B and C. So you fix your character basically up to constant multiple. And you find an index set, a pair of integer points, a set of integer points in the plane which has that BC in its strict convex hull. So you have BC here. Here's BC. And now you find find some points that are integer points that are in a strict convex hull. And you find them from the coordinates of the variables you have. You take the complement of that in your set of coordinates. And then you take the columns of B corresponding to the complement. And that gives you a complement in R9. That's, you add up all such columns and you get a fan, which gives you the torque. So here, we organized our coefficients in this little 3x4 matrix. And this is the ij's, right? That correspond to what was left. This stuff, there's nothing over here because there's a tack node. We eliminated this guy here by making the Turnhouse transformation. So here are the 12 possible integer points you use for the index set I. And now you choose a BC somewhere in here, throw down a dart at this thing and you get a BC, and then you say, okay, well, what are the I's which have that BC in its strict convex hull? And for every time you can say yes to that, you take the complement, you take those columns of that matrix B, gives you a column, and you organize all those columns into a fan. And turns out it's a complete thing. And that's, it turns out, now what we were able to prove is that if you choose your BC, well, first of all, if you choose your BC outside of the quadrilateral, there's no complement. It's not in a strict convex hull of any subset. So you have to be inside the quadrilateral. And the theorem that we're able to prove is that this, if you choose your BC in this green part, this little green strip on the sort of south and west part of the quadrilateral, this is a compactification of the other quotient. It's a compactification of the other quotient. If you cross over, you get other quotients which are not compactifications of the first one we construct. But there are hundreds of possible quotients here. Let me show you one. Let me show you the picture. So here's, we sort of organized this southwest part here, colored it in, but you can choose any BC in this picture. And depending on where you are in this, every one of these has a different set of strict convex hull answers. Every one gives a different column. There are hundreds of quotients here that are available to construct this quotient space. We think the ones that are of interest are over here. You also see very clearly, we worked this out in the paper, how passing from one region to the next, it crosses a wall. It is basically the sort of wall crossing phenomenon in modular spaces. Perform some sort of flip. Basically, you're taking two cones that are oriented in one direction and replacing them with two cones that are oriented with another direction. And when you actually cross and are on the line segment, then you have a cone which is you have a support set. This I only has 2 elements, so the complement is 10. So it's not it's still a polyhedral cone. It's not a simplicial cone. So that crossing, you cross from one to another by introducing non-simplicial cones into the analyses of the module. So we analyzed very, very carefully what's going on in the southwest region. All of these compactify the other ones. We don't know what's going on. Let's go into that yet. Just by chance, Alina posted a preprint on the archive this morning, so I'm not checking your email, but you can read the paper as of today. So I think that might be my last slide going back to this. Yeah. So some future questions are the following. Can we do anything similar for higher n? When n is 3 or more, you will not have a double cover, such a nice double cover representation of your rational elliptic surface. So that trick goes out the window. I know exactly what trick to use. So that's one direction to take this. Another direction to take this is to relax the requirement that you're adding this bisection marking to the problem. So what if you just try to look at moduli of rational elliptic surfaces, period, without the extra data of the marking? What can you say about that moduli space? Can be constructed explicitly? There are ways to approach this, but they're more along the lines of what Alina did already. And it's you get sort of stability answers, but you don't get an explicit construction in terms of more it's the things like a toric thing. So those are two directions that we can take this into. So thank you very much. Thank you.